Hello, everyone. We're going to go ahead and continue on with our standard 5 work here on normal distributions by talking about what a z-score is. A z-score, by definition, is how many standard deviations from the mean a given value is. And for our formula here, z equals the value x minus the mean mu divided by the standard deviation sigma. So before we talk about how we can use the z-score, let me pose this question for you. You take two math tests. On test 1, you score a 90. On test 2, you score a 75. And your question is this: on which test did you do better? On which test did you do better when compared to your class? Now, that we really can't answer because we don't know the results when compared to our class. I don't know how atypical my test score of 90 and 75 are when I compare them back to the results from my class. Now, obviously, we can see that, from just a numerical standpoint, 90 is better than 75. So you might be, prone to answer, say, I did better on test 1. But what if everyone aced test 1 and you got 90? You did poorer than that. You didn't do as well. Or what if test 2, 75 was a pretty good score because everyone else failed it? That might be a pretty good test result, even though you did better than you did worse than when compared to just test 1. That's where z-scores come in. They compare our data point to the rest of the distribution, given the mean and standard deviation. They'll help us tell how atypical our given value is. So let me ask you this. Let me tell you this here. Say for test 1, the class average was 80. And on test 2, the class average was 65. And I say, all right, now I give you the average. You should be able to tell me on which test you did better. But we still really can't because on each of these two tests, you did 10 points better than average. So you might be saying, all right, well, I did just as well on both of them, but that's, still only part of the story because I don't know how spread out the results were for these two tests. Maybe everyone really got close to the average score of 65 on this, so 75 is a really, really good score because there was less error, there was less variance or spread. Maybe that was the case here. Maybe everyone got really close to a score of 80, so your test score of 90 is more of an outlier. So let's say that the standard deviation for test 1 was 3, and for test 2, it was 1. So now, on which test did you do better when compared to your class? And the answer is on test 2, because most people got a score closer to 65, which means that your score of 75 is a more extreme outlier. You still did 10 points better here, but there was more spread in the test scores. So your test score of 10 points better than average isn't as rare as it would be for on test 2. And that goes back to our z-score formula. The z-score tells us how many standard deviations from the mean a given value is. It kind of puts everything on the same scale. It tells me how atypical a given data point is when compared to the rest of a normal distribution. So for test 1, our z-score is this: how many standard deviations from the mean a given value is. So let's first figure out how far from the mean our test score was. 90 minus 80, and then divide by, to put it in terms of the standard deviation, 3. That's 10 divided by 3, or 3.3 repeating. For test 2, our z-score would be the same setup, 75 minus 65. We're 10 points better than average, but there's less spread. My score of 10 points better than average is much more uncommon because there is less variance, less spread in the distribution. A z-score of 10 is much more atypical than a z-score of 3.3 repeating. So we did better on test 2 when compared to the rest of the class than on test 1. So let's use that to answer a few questions here. We're going to look at this setup. The ACT composite has an average score of 20.8 and a standard deviation of 5.8. So this is some helpful information. My distribution has an overall average score of 20.8. with a standard deviation of 5.8. And let's use that to draw the normal distribution. If all else fails, make a picture. We're going to see what percent of ACT scores were greater than 28. So I'm going to draw the part of the distribution that is greater than average. We're going to start at 20.8 and do 1, 2, 3 standard deviations above the mean. Every time I move to the right 1 standard deviation, I'm going to add on 5.8 for that composite score. So here's 26.6, 32.4, and 38.2. What we're looking for is the probability that we got an ACT score that was greater than 28. Greater than 28 would be right here on that number line. And I want the part shaded to the right, greater than that. This would be a value that we can't find using the empirical rule, 68, 95, 99.7, because our score of 28 does not land on precisely 1, 2, or 3 standard deviations above the mean. We're going to have to use a z-table here in a moment. But first, let's find how many standard deviations above the mean a score of 28 is. So we first need to figure out how much above the mean. Well, that's 28 minus 20.8. And then in terms of the standard deviation, we'll divide by 5.8. So 28 minus 20.8 divided by 5.8 is a z-score of 1.24. Which makes sense given our picture below. Here's the middle, or the average, and we are 1 and a little more standard deviations above the mean, approximately 1.24. So what we need is the probability of a z-score that is greater than or equal to 1.24. This is where a number table comes into play. Our z-table will look something like this. A z-table gives us the relative probabilities for all sorts of different z-scores. And by default, it's going to give us the probability of for the part of the distribution that is to the left, lower than, into the left tail, as you can see in the picture here. So on a z-table, these columns give us the sign. We see negatives here for below the mean, the ones place and tenths place for the z-score. So all of this row is the z-scores and probabilities for negative 2.6. If I want negative 2.65, that would be this column here. The columns are the hundredths place. And I can see that 0.004 is the proportion of the normal curve that has a z-score more extreme than negative 2.65. Since we wanted 1.24, we're going to flip over to the next page. 1.24 would be 0.8925. But now be careful. On the picture, I drew the curve to the right. 0.8925 gives me the distribution to the left. But this is easy to find our final answer because I know that everything under the curve has to add up to 1. The area of the entire distribution, the area under the normal curve, must add up to 1. If this is 0.8925, the tail to the right, the other part, is just 1 minus 0.8925. So 1 minus 0.8925 is 0.1075. Now we can find this using Desmos as well. I've got it set up to be 20.8 and 5.8 are given mean and standard deviation. and I want the part above a score of 28. So let's put a minimum score of 28 and get rid of that. We can see the right part of the distribution has been shaded over here in the graph. There is a little bit of rounding error using by the z-table by hand and the Desmos calculator, but it's approximately the same thing, about 0.1075. For part B, I want the percent of ACT scores that are lower than 17. Well, let's go ahead and find another z-score. Lower than 17, so x minus mu divided by sigma, using the same standard deviation and mean from before. 17 minus 20.8 divided by 5.8. Gives me a z-score of negative 0.66. So let's go to the z-table and find what proportion would fall to the left of a z-score of negative 0.66. Negative 0.66. Here's negative 0.6. 1, 2, 3, 4, 5, 6. Since the z-table was designed to give me the area to the left, I want ACT scores that are less than 17. Here's my final answer. I do not need to subtract from 1 because I want the part to the left, which is given on the z-table, not the part to the right, the greater than portion, 0.2546. The probability of a z-score less than or equal to negative 0.66 was 0.2546. And we can find that on Desmos. We're going to get rid of this, make the minimum negative infinity, and a maximum of 17. About 0.2562, roughly the same result we got, shading the tail to the left. Lastly, for part C, I want the percent of ACT scores between 15 and 23. Notice now I want between. So this is going to require two different z-scores because I have two different test scores, 15 and 23 given. We're going to subtract the proportion between the two for our final answer. Let's start with the 23. Z equals 23 minus 20.8 divided by 5.8. Means I am 0.40 standard deviations above the mean. Next, we need 15. So 15 minus 20.8 divided by our standard deviation of 5.8. Let's see, I'm 5.8 score below the average. So negative 5.8 divided by 5.8 means our z-score is negative 1. Since I want the proportion between, we need to find the probability of our z-score being between negative 1 and 0.4. So let's look up the proportion of the normal distribution for each of these and then subtract using the z-table. 0.4 is 0.6554. Everything that is 0.4 and to the left accounts for 65.54%. So we'll write that down. Now let's go ahead and look up the proportion for a z-score of negative 1. Negative 1 is 0.1587. Everything in the left tail less than a z-score of negative 1 accounts for 0.1587 of the normal distribution. to find the area between the two, because remember, I want to find the percent of ACT scores that are between 15 and 23. Well, if 0.6554 is 0.4 or less on the z-table, if everything with a -1 z-score or left is 0.1587, the part between the two is just the difference. So 0.6554 minus 0.1587 gives me 0.4967. So about half of all ACT scores are between 15 and 23, 49.67%. We can find this on Desmos by setting our min and max to 15 and 23. They had a final value of 0.4891, which is approximately the same result we had. Notice that I'm shading in this middle portion here, about half of the normal curve. The z-score kind of puts everything on the same scale. It tells us how atypical, how far from the mean in terms of the standard deviation a given data value is for our normal distribution. So I think we'll call that there. Have a good one, guys.